in that gigantic electrical grid that powers our entire world, things can and do go wrong. It could be anything: a lightning strike, a tree falling on a line, or just some equipment getting old and failing. And when that happens, it can unleash this sudden, absolutely massive surge of current. That surge is what we call a fault current. And believe me, understanding it is critical to keeping our lights on and our systems safe.
Just picture it: a sudden, blinding flash on the power grid. In that single instant, something has gone very wrong. We call that a fault. So instead of electricity flowing where it's supposed to, it takes a dangerous shortcut. This creates a surge of energy that can be thousands of times bigger than what the system was ever built to handle. Figuring out how to predict and handle that surge, that's one of the most important jobs in all of electrical engineering.
So in this explainer, we're going to dive deep into the world of fault currents. We'll kick things off by defining what a fault even is and why we have to analyze it so carefully. Then we'll get into the different kinds of faults you'll see, learn a bit about how engineers calculate their incredible power, and finally, see how all this knowledge is put into practice to protect our electrical systems.
All right, so let's start with the absolute basics. What exactly is an electrical fault? Well, simply put, it's any weird, abnormal condition that messes up the normal flow of current in a power system. And that brings us right to our main topic: fault current. See, this isn't your regular, everyday electrical flow. It's a massive, instantaneous surge that happens during a fault. Imagine electricity is like water flowing in a pipe. A fault is like a huge hole suddenly blowing open in that pipe. That water, or electricity, is going to rush out of that new, easy path because there's almost nothing stopping it. In electrical terms, we call that a path of very low impedance.
Let's just stick with that water pipe idea for a second, because it works really well. Normally, the water's just flowing along, but if a giant crack opens up, whoosh, the water gushes out through that new opening. Electricity does the exact same thing. When a fault creates an easy path to ground, for instance, the current just rushes through it. And that's the key takeaway here. The lower the impedance, the higher and way more dangerous the fault current becomes. Okay, so these currents are huge. We get it. But why is it so incredibly important for engineers to be able to calculate exactly how big they'll be? Well, the answer really boils down to three things: safety, coordination, and the simple survival of the electrical grid itself.
You see, fault current analysis is really the foundation of all electrical safety design. It tells us what kind of specs we need for pretty much every piece of protective gear. For example, a circuit breaker has something called an interrupting rating. That's its ability to safely stop a huge current. Well, that rating is set by the biggest possible fault current that breaker could ever see. And the same logic applies to choosing fuses, building strong bus bars, and setting up our protective relays.
And this really highlights what's at stake. Let's say your calculations show that a fault could produce 40,000 amps at some point in your system, but the circuit breaker you installed there is only rated for 20,000 amps. What happens? Well, that breaker won't just fail, it could literally explode, and that can cause a catastrophic failure, leading to huge power outages, or even worse, a serious accident. The whole point is to make sure every piece of equipment can survive long enough for the protection system to do its job and isolate the fault. Now, it's really important to get this. Not all faults are created equal. Engineers actually classify them into a few different types because each one acts a little differently and needs its own specific kind of analysis.
There are really four main types we need to know. First, you have the three-phase fault. That's usually the most severe, but thankfully it's less common. Then there's the single line-to-ground fault, which is by far the most common one you'll see. And finally, you have the line-to-line and the double line-to-ground faults.
And here's a really crucial distinction. A three-phase fault is what we call symmetrical. That's because it affects all three power phases equally, so the system stays nice and balanced. But those other three types, they're unsymmetrical, and they create a serious imbalance. So why does that matter? It matters a lot, because that imbalance makes the calculations way more complex. This whole distinction is fundamental to picking the right method to analyze the problem.
So how in the world do engineers actually go about calculating these massive currents? This is where we get into the heart of what's called short circuit analysis. It's a mix of some basic principles and some really clever mathematical tools.
So first things first, you have to model the system. Every single component, from the generator creating the power, through the transformers, and all along the power lines, every single one has some natural impedance that acts kind of like a bottleneck. It's the total impedance, from the source all the way to where the fault happens, that ultimately puts a cap on how high that fault current can get. And really, this all comes back to a principle you probably already know, Ohm's law. The fault current, I, is just a system voltage V divided by the total impedance, Z. So the formula itself is pretty simple, right? The real challenge is accurately calculating that Z value in a huge, complex, interconnected power grid.
To deal with all that complexity, engineers use a really clever trick called the Thevenin equivalent. What this method does is it lets them take that entire massive power grid and, from the perspective of where the fault is, simplify it all down to just one voltage source and one single equivalent impedance. It's a brilliant shortcut that makes the calculation manageable.
But what about those tricky, unsymmetrical faults we talked about? For those, engineers have another powerful tool in their belt called symmetrical components. Think of it like this. Imagine you have a really complex, tangled-up knot. Instead of trying to undo the whole thing at once, you figure out how to separate it into 3 much simpler, neater knots. You solve each of those, and then you combine the answers to solve the original, big knot. That's pretty much what symmetrical components lets us do for these unbalanced electrical systems.
Okay, we've done the analysis. We've crunched the numbers. Now let's bring it all back to the real world. Let's talk about the actual hardware that keeps our lights on and stops disasters from happening.
You know, when a fault happens, this incredibly fast, automated sequence of events just kicks right in. First, the fault occurs. Instantly, a protective relay, which is like the brain of the system, detects that huge surge of current. That relay immediately sends a trip signal to a circuit breaker. The breaker then physically opens up, interrupting the flow of current and isolating the faulty part from the rest of the system. And this all happens in just a fraction of a second.
And it's the results from that fault analysis that make this whole super fast sequence possible. Those calculations are used to pick breakers that can actually handle the massive current. They're used to coordinate the relays so that you only have a small outage instead of a big one. And maybe most importantly, they're used to calculate something called arc flash hazards, which helps keep the electricians who work on this equipment safe.
So at the end of the day, the entire reason we do fault current analysis is to make sure that when a fault happens, and it will happen, the system is ready for it. It has to be fast enough and strong enough to contain the problem safely. It's all about preventing a small issue from snowballing into a widespread blackout or a catastrophic failure.
And all this leads to a final, really important question. You see, our power grids are changing fast. We're adding in all sorts of renewable energy, smart grid technology, and more complex connections. So as this grid continues to evolve, how do our methods for calculating, predicting, and protecting against faults need to change to keep up?